Today we'll start new section 4.6 about area between two curves. So recall that at the beginning of this chapter we discussed the area problem. So suppose you have some function f of x and it gives you some graph, and say you are interested in the area under this curve between two vertical lines, x equals a and x equals b. So in this one, in that section, we discussed, this is my f of x, we discussed that it corresponds to the definite integral from a to b, our function dx. How can we interpret this integral? So remember that by the definition, its limit when n goes to infinity, summation f at some points of xi times delta x, I runs from 1 to n. So we divided our interval from a to b into small subintervals and approximate our area by rectangles and then sum them up and then consider the limit when the length of interval goes to 0 while the number of intervals goes to infinity. And we got the definition of definite. So this is kind of remark that will be quite useful. This part of the integral, it corresponds to the summation of small areas of rectangles. While this part, f of x times dx, it's what is called typical element. F of x dx. And it represents, in fact, just the area of the standard rectangle. So we choose this rectangle, then its base will be dx, while its height will be f of x. So indeed, this typical element gives me typical area of a rectangle. Or in other words, area of typical rectangle. And so indeed, when we combine this integral and f of x dx, so if we think about them as separate objects, then we indeed get sum of areas of typical rectangles. Another way how you can think about integration. Let's do one example. Suppose you have function y equals square root of x, and you are interested in the area of the region bounded by this function, x equals 4 and y equals 0. So what do we have? We have the following picture. Here is my square root of x. Then I have somewhere here 4. And my y equals 0 is just x-axis. So I'm interested in this area. And you can think about integration, again, using this correspondence in the following way. So first, choose some typical element. So let's draw some rectangle here with base dx, and the height will be f of x again. So typical element will be f of x dx. But in our case, our function is square root of x, so it's square root of x dx. And now we should sum up the little areas of such rectangles from 0 to 4. and that gives me this operation from 0 to 4. So I'm summing the little areas. From 0 to 4. And so I obtain that my area thus will be the summation of typical elements, which are square root of x times dx. So in other words, I again obtain that my area is just the definite integral of the corresponding function. And of course, I can calculate it. So I can write that it is the same as integral from 0 to 4 x to the power 1/2 dx, and then use our rule that we discussed last time. So it's x to the power 1/2 plus 1, or 3/2 over 3/2, and substituting from 0 to 4. And so I get 2/3, 4 to the power 3/2, or it is square root of 4 to the power 3 minus 2/3 times 0. And so it is 8 times 2, and finally it's 16 over 3. So nothing new so far, just another way how you can think about integration. And in fact, this is a special case of a more general problem, finding areas of regions bounded by two curves. So area under the curve is just area between our curve and x-axis. But in general, you have the following situation. You have two functions. Like that. And you're interested, and this is your y equals g of x. And you're interested in the area bounded by these two curves and vertical lines x equals a and x equals b. And in fact, you can repeat the same steps that we did. So let's introduce typical element. So let's choose some rectangle here. So this is my typical element. It's still a rectangle, but now, even though the base is the same, say dx, but now my height is of course not just f of x, so it's a rectangle with the base that equals dx, but now the height is equal to what? So it is f at point x minus g at point x, as you can see from the picture. And so I get that my typical element is equal to f of x. So my typical element is rectangle, but the area of that rectangle is f of x minus g of x times the base, which is dx. And now again, I'm summing up all such areas of small rectangles, and that will give me approximation of my area, and then I consider the limit when n goes to infinity or length of subintervals goes to 0. So I'm summing up them. Again, summing the little areas. Thus, my area becomes the following integral from a to b, f of x minus g of x dx. So I'm summing areas of typical elements. And that gives me this formula. And this is a formula for the area between two curves. So we can formulate it as a theorem. So what you need to do? Need to draw a typical element of thickness dx. But now between f of x and g of x. Then sum the small areas which are f of x minus g of x times dx by operation integral from a to b. And we will obtain that the area is equal to integral from a to b f of x minus g of x dx. In the proof of this statement, we use the fact that f of x is above g of x. So in this, so if you have just two curves, first of all, you should determine which one is above. And that will be your function f of x, while the function which is below will be your g of x. So you should subtract smaller from the bigger one, because your area is a positive number, while if you integrate something negative, you will obtain negative. So we can see it in a following example. Find the area bounded by the curves y equals minus 1/2 x, x equals 1, and the x-axis. And so what do we have? We have the following picture. And so I'm looking for the area of this region. If I just try to naively integrate it, what I'll get? I'll get, so integral from 0 to 2 minus 1/2 x dx. So I can put constant in front of the integral, minus 1/2 integral from 0 to 2 x dx. And this integral gives me x squared over 2, substitute from 0 to 2. And so on the upper limit, I'll get minus 1/2 times 4 over 2, which is 2, while on the lower limit, so it's minus 1/2, so it's plus 1/2, but it's just 0, and so it's minus 1. So we get that if we do it naively, then the area is negative. Of course, it's not true. And in fact, in this case, you should think about this as part of the general problem, as an area between two curves. One curve is minus 1/2 x, and second one is y equals 0. So this is your second curve. And so, as we discussed, we should integrate function which is the difference of two functions, and the first one is the function which is above second one. Correct way is the following. So either you do the same steps as we discussed before, so you introduce some typical element, and typical element will have base, that is dx, while the height will be what? 0 minus value of my second function, so minus 1/2 over x. And so height thus will be 1/2 over x. And so I should sum up using this part of the integral from a to b, which is from 0 to 2, sum of the areas of typical elements. And the area in this case will be 1/2 of x dx. So you see now I don't have here minus. This is one way how you can obtain the correct answer. Another way, as we discussed, you can say that it's indeed area between two curves. One curve is y equals 0, and this curve is above the second one, which is minus 1/2 x. So you can write it as 0 minus 1/2 x dx. Of course, you'll get the same. And so you got 1/2 you can put in front, 0 to 2x dx, basically the same calculation, but now you will obtain 1, because now there is no minus in front of that. And this is the correct answer. So there is kind of side remark. So if you have a function, but it looks like this, part of the function is below x-axis and another part is above, then integral from a to b, your function f of x dx, will give you, so this area I will call a1, and this area I will call a2, will give you a1 but with minus and a2 with plus. So everything that is below x-axis, your integral makes negative. So thus there is no surprise that when we try to calculate the area just using one function, then we obtained -1 because it's minus value of the area. And this picture also shows what you need to do if the curve crosses the x-axis. So part of the region lies above the x-axis and part of the region below. You should split your integral into two. What I'm saying, that you should use this property of the integral that says the following, that if you have integral from a to b f of x dx, then it's the same as integral from a to c f of x dx plus integral from c to b f of x dx. And of course, you should assume that f is integrable on all these three intervals, on interval ab, on interval ac, and on interval cb. And in fact, we have seen this property before, and it represents a very simple fact. Of course, that you need to prove, but from the picture, it's straightforward. If you have some function f of x, and you have 2 points, a and b, and some third point, in general, it can be inside interval ab or outside, but let's, for simplicity, put it inside. Then integral from a to b is this area, while integral from a to c is blue area, and integral from c to b is red area. So indeed, sum of two pieces gives you the whole piece of area. But using this property, you can indeed solve that issue if your function crosses the x-axis. So let's do it in the following example, number 3. So find the area of the region bounded by y(x) equals x cubed, x equals -1, and x equals 2. Okay, and the x-axis. So let's draw the picture first, something like this. And I'm interested in area bounded by this curve, x equals -1 and x equals 2. So this is my area that I'm looking for. And from the picture, we indeed see that we have a problem because part of our region is below the x-axis. But we will use this property, what is the area between two curves? So the area between two curves, say f1 of x and f2 of x, is the following integral: difference of f top of x minus f bottom of x dx, where f top of x is above f bottom. And in this case, we see that on the interval from -1 to 0, so we have two curves. One is our y equals x cubed, and another one is y equals 0. So we have two curves, but on the interval from -1 to 0, the top one is y equals 0, because y equals x cubed is below that. While on the interval from 0 to 2, my top function is x cubed, while the bottom function is y equals 0. And so that's why I need to split my integral into two parts. So on the first part, my top one is y equals 0, and on the second part, my y equals x cubed. So my area that I'm interested in will be integral from -1 to 0. Again, let me write it in this way: minus f bottom of x plus integral from 0 to 2, the same f top of x minus f bottom of x. But as I said, on the interval from -1 to 0, my f top is y equals 0, while and f bottom thus will be y equals x cubed. While on the interval from 0 to 2, my top is y equals x cubed, and my bottom is y equals 0. So they switched. And finally, what I'll get? I'll get that my area is equal to integral from -1 to 0, 0 minus x cubed dx, plus integral from 0 to 2, x cubed minus 0 dx. And so what I'll get? First one gives me x to the power 4 is minus over 4, substitution from -1 to 0, plus second one gives me also x over 4, x to the power 4 over 4, substitution from 0 to 2. And so it is, on the upper limit, I got 0 for the first part. On the lower limit, I got minus 1 over 4. 1 minus because of this one, and another minus because I need to substitute the value on the lower limit. While the second one gives me 2 to the power 4, it is 16 over 4, which is 4, and on the lower limit I got 0. So finally I'll get 1 over 4 plus 4, which is the same as 17 over 4. Yes, so you see that first part, so the first integral gave me value 1 over 4, which is positive. So indeed I obtained area. While if I just integrated y equals x cubed, I will get negative number. So that's what we can see if we just integrate naively x cubed dx from -1 to 2. So it will be x to the power 4 over 4, substitution from -2 to 2. And I'll get 4 minus 1 over 4. So the same 4 I have here, but instead of plus 1 over 4 that I get here, I get minus. So that means that indeed my integral counted this piece from minus 1 to 0 as negative 1. So I obtained 15 over 4, which is of course not the same, but it still has the following meaning, that it is this area with plus and this area with minus. Sometimes it's also useful, but it's not about the area under the curve. So it is A1 minus A2. Okay, and sometimes you don't have limits of integration and you need to find them. So let's do the following example. Find the area of the region bounded by the parabola y squared equals 4x and the line y equals x. So let's again draw the picture. So you can either think that y is equal to plus minus square root of 4x, or you can think that x is equal to y squared over 4, which is the parabola. So either this or that gives you the following. So it looks like this. This is my first function. Not, in fact, it's not a function, it's a curve, because for one x, I have two values of y. But it's still some curve. And second function is y equals x. This is my y equals x, and this is my y squared equals 4x. And so we see that indeed there is a region that bounded by these two curves. And so in fact, we don't interested in the part which is below, only in the part which is just plus square root of 4x. But we still don't know the coordinate of this point. So this is probably 0, but how to find that one? And as we discussed, you just need to solve simultaneously these two equations. So to find the coordinates. So you have that y is equal to x and y squared is equal to 4x. So in some sense, it's the solution of the system, but it doesn't really matter here because what you'll get, that y squared is equal to x squared because of the first equation. And because of the second, y squared is equal to 4x. And so you get that x squared is equal to 4x. And you can write it in this way, that x squared minus 4x is equal to 0. And if you factorize it, you get that x times x minus 4 is equal to 0. And that gives you that either x equals 0 or x equals 4. And so that gives me these two coordinates. So this one is 0, in fact, and this one, in fact, is 4. And so I found my limits. And the last step is, again, we should integrate f top minus f bottom. And the top function in this case is square root of 4x, while the bottom one is y equals x. So thus, area between these two curves will be integral from 0 to 4. Top one is square root of 4x minus bottom one, which is x. And what I'll get? I'll get that it is integral from 0 to 4. Square root of 4 is 2. So I can put it in front of the integral, and square root of x is x to the power 1/2 dx minus integral from 0 to 4 x dx. And so first gives me 2 times x to the power 1/2 plus 1, which is 3/2 divided by 3/2. And minus integral of x gives me x squared over 2. And I should evaluate this from 0 to 4 and this one as well from 0 to 4. So at 0 I get 0, so I'm interested only in upper limits. So it's 2 times 2/3 times square root of 4 to the power 3. That is the first one, and minus 4 squared over 2. It is 4 over 3 times square root of 2. Square root of 4 is 2. 2 to the power 3 gives me 8. And minus 16 over 2. Oh, it's better to write it as 16 over 2, which is 8. And so if I, again, make the common denominator, it will give me 32 over 3. And 8 is the same as 24 over 3. And the final answer is 8 over 3. Let's do another example. So far we have used letter x for the independent variable and y for the dependent variable. But of course, it's the usual convenient, but sometimes it is better to use y as a function of x, especially when x in terms of y is a simple function, while y in terms of x is something complicated. So if you have, say, x equals y cubed minus 3y plus 1, then y as a function of x is complicated, right? You need to solve cubic equation, while x as a function of y is already given. It's y cubed minus 3y plus 1. You don't need to do anything. And sometimes when you have such situation, it's easier to integrate with respect to y, not with respect to x. And that's what happened in the next example. Find the area of the region bounded by x equals 8y minus 2y squared and the y-axis. So what do we have? If you draw your curve, so it's parabola in terms of y, and it will look like this. But since you are interested in only in region bounded by this curve and y-axis, so this is your second curve, y equals 0. In fact, you don't care what happens further. And this is your x equals 8y minus 2 y squared. So how to sketch this curve? First of all, you understand that it should be a parabola, and then you can factorize it in the following way. So it's 2y times 4 minus y. And you see that there are zeros when y is 0 or y equals 4. And that gives you these 2 points. So 0, and this point is 4. And that's how you can graph this parabola. You can do it more accurately, and we discussed in the previous sections how to use first derivative, second derivative, and so on to sketch your curve. But in this case, we just need very rough sketch. Of course, you can try, in this case, you can try to express y in terms of x, but then you need to solve quadratic equation and then integrate something that contains square root, and so it doesn't look very nice. But instead of that, let's try to repeat the same steps that we did at the beginning with typical element in this case, but let's do it horizontally. So what I'm saying, let's split this area into small rectangles like this. So this is my typical element. That was small rectangle, but now it's not vertical, but horizontal. What about the area of this rectangle? So before, we split our interval from A to B into small pieces, but interval AB was X interval, while here I have Y interval. So my base now it's not dx, but dy. So this small. And what about the height? Height, if you rotate this picture, you can see that height is in fact just the value of x as a function of y. Right? So I have some y here, and the corresponding height is the value of my function, but it's x value. So it's x of y. So this is first option. And the second option is x as function of y. And in this case, I get that area of the typical element is, so its base times height, or better say height times base, it is x of y dy. And this is important. So before it was f of x times dx. Now we in some sense switched x and y and got that it is x of y times dy. And then again, I need to sum up all these areas. But now, again, my limits are y limits, because now y variable is running. And so my limits for y are exactly these 2 points, 0 and 4. So I'm summing up these rectangles from 0 to 4. And my typical, the area of my typical element is x of y dy. But my x of y is this function 8y minus 2y squared. And so I get that it is integral from 0 to 4, 8y minus 2y squared dy. And again, I obtain just a polynomial that's easy to integrate. And so I get, so first gives me 8 times y squared over 2. Second gives me 2 times y cubed over 3. And I need to substitute from 0 to 4. So it's 0, and you can check that if you plug y equals 4, then you obtain 64 over 3. And this is the final answer. So this is remark. If x as a function of y is simpler than y as a function of x, then we can calculate area using this formula. It's integral from y naught to y1 x of y dy. So it's another formula for the area. Yes, and in fact, we can repeat the same steps in this case and obtain the area between two curves that are expressed as a functions of y rather than x. So example number 7, find the area of the region bounded by curve x equals y squared minus y minus 2 and y equals x plus 2. So you see, first equation has the following form, x as a function of y, which is y squared minus y minus 2, while the second one has form that y equals f of x, where f of x is x plus 2. So in some sense, we have a mix. But we see that the transformation of this function to function x as function of y is much easier than the transformation of this equation to the form y is function of x. Because again, here I will need to solve quadratic equation and try to express y in terms of x, while here it's just one line. So my x from this equation will be y minus 2. And so again, I obtain the form x as a function of y. So in this case, it's easier we see that we should use indeed form x as a function of y. And again, we can draw the picture. First function is a parabola in terms of y. And what are the zeros of this parabola? So again, I need to solve y squared minus y minus 2 is equal to 0. And that gives me y equals 2 and y equals minus 1. These are the roots. So I have 1, 2, and minus 1. And so it will look while the first function y equals x plus 2 or x is equal to y minus 2, it's just straight line, goes through points 0, 2 and minus 2, 0. In fact, it passes through the same point 0, 2. And I see the bounded region, which is this one, between two curves. And let's apply the same trick as we did. So let me zoom this part. Let's consider the typical element, but again, a horizontal typical element, because as we discussed, that in this case we have x in terms of y. So we should integrate with respect to y. And so here's my typical rectangle, like this, and base is just dy, while the length, so this is my x equals y squared minus y minus 2, while this line x equals y minus 2. And let's call it x1, and this will be x2. And so we have this horizontal typical element with base dy, and the length of this element will be what? For this y, I have corresponding x. Let's call it b. And also I have, for the same y, I have this point, let's call it a. In general, it can be not minus 2, but just some point a. And so my length thus will be the same as the length of interval AB. But the length of this interval is b minus a. But b is x2 at point y. So here's my y. While a is x1 at the same point y. So I get that my length is equal to x2 of y minus x1 of y. And thus, my area is summation of such typical rectangles, so it's integral, and I integrate with respect to y, so I integrate from 0 to 2, area of the typical element, which is length of my typical element, or x2 of y minus x1 of y times the base, which is dy. And so I obtain this formula, And now I can substitute that my x2 is y minus 2 and x1 is y squared minus 1 minus 2. So it gives me the following integral from 0 to 2, y minus 2, which is my x2 of y, minus y squared minus y minus 2, which is my x1, times dy. And so I can simplify it and get integral from 0 to 2 minus y squared plus 2y dy. And the integral thus will be minus y cubed over 3 plus y squared, substitution from 0 to 2. And you can check that it is 4 over 3. So let me make one remark that thus we can say that the area between two curves that are expressed in terms of y, so x1 of y and x2 of y, is given by this integral. So remember, when we integrated with respect to x, we had f top minus f bottom, while here we see that we have integral of one function which is to the right of another. So x2 is to the right of x1. So in other words, I have integral from some 0 naught to 0 1 x right of y minus x left of y dy. And this is also useful formula.